Greetings and welcome, friends. Mr. Waddy here, back, rejuvenated from a vacation. We're talking about a new section. We are graphing today f of x equals, specifically, x squared plus c. We'll deal with this little a fella tomorrow. We're technically mostly in section 8.2 today, but we'll also be pulling some stuff from 8.1. I blended these together to be what I feel is a more effective way of looking at these. So it says this: sketch the graphs of the functions in the same coordinate plane. And what do you notice? So first of all, let's graph f of x equals x squared. All right, so let's make a little xy table, or x and f of x chart here. And it looks like I've got some negative x values and some positive x values. So let's plug in some of each. Let's do -4, -3, -2, -1. Tyler, 0, 1, 2, 3, and 4. Let's see how far we can go here. So let's see. I'm going to start with the easy one. If I want to plug in, because f of x is equal to x squared, remember, if I want to plug in 0 for x, what do you guys think 0 squared means? 0 squared. What's 0 times 0? Is going to be 0. All right, so I'm going to plot that point. Actually, I'm going to even do this in a different color. So that means the point 0, 0 is on my f of x graph. If I plug in 1, what is 1 squared, or 1 times 1? 1 times 1 is 1. Yeah. So that means the point 1, 1. So over 1, up 1. Oh. Well, let's hold off on the negatives. So we've got a theory. Is -1 squared equal to -1? Is the current conjecture. Well, let's try 2 first. What's 2 squared? 2 times 2. 2 times 2 is 4. So that means the point 2, 4 is going to be on our little graph. So over 2 and up 4. Like so. Wait a minute. Guys, what is this graph doing? If I drew a line, it would only hit like 2 points. Oh, wait. Oh, maybe it's this line. Oh, no, but now it doesn't hit that one. Guys, this is a weird graph. Interesting. Yeah, it's a different type of graph. It's going to be a curve and not a line. Let's see, let's try 3. 3 squared is 9. 3 times 3 is 9. And actually, we won't go as far as 4. It won't fit on our graph, our graph. So over 3, up 9. Looks like it lands right there, right, Tyler? You're with us. Mr. Waddy's rejuvenated after vacation. Some of us are still a little bit more restful. Resting, maybe, is what I meant. But getting used to the sleep schedule all over again is always tricky. I woke up at like 4 in the morning, and I was just like, I'm ready. And I like already had my white shirt and tie on. That's actually a lie. Actually, I realized this is pretty much SpongeBob colors I'm wearing today. Wow. Not bad. Not bad. Also, I didn't mean to wake up that early. It was an accident. Not that I like had an accident and like peed my bed. I accidentally woke up that early and then couldn't fall asleep. There we go. All right. So anyways, wow. All right. Now, how about that -1? All right. -1. Now, -1 all squared means -1 times -1. So it's going to be +1. So that means the point -1 for x and +1 for y is going to be right here. What do you guys think -2 all squared will be? So -2 all squared will be +4, because a -2 times a -2 is a +4. So if I go from the origin, left 2, and up 4, there we are, like so. And -3 all squared, what's your guess? +9, yeah. So -3 and up 9, like so. And so it looks like these points are kind of mirrored versions of these other points, right? You see that? How they're mirrored? What line are they being mirrored over? Or what axis, should I say? It looks like this one's 3 units away from that, right? 3 units, 2 and 2, 1 and 1. This one's mirrored onto itself, I might argue. What axis, what line are they being mirrored over? Yeah, the y-axis, right? Here's the y-axis. And that is going to be one of the things about these new types of graphs. They are symmetric over a line. They're a mirror image of themselves. Kind of like back when we were graphing absolute value. Did we do that? Yes, we did. Yeah, we shifted the v function. This one's going to be a little bit more U-shaped. So this is not going to be a pointy bottom here. The graph is going to look something like this. I'm going to do my best. Oh, you know what would have been cool? Let's see. It's going to be so cool, I'll take the lazy time to do it. Here we go. I've got this. Oh, darn it. Here we go. Here we go. Watch this. Watch this. I can actually make a mirror line. And let's see how well. So I can actually. Whoa! Right? Look, that's like a weird goat. I can actually. Let's see. And I can draw 2 curves at once. And so this graph is a little bit more U-shaped. It's called a parabola, right? Which Brandon, you'd already said. Parabola is the name of that curve. And it gets steeper and steeper, faster and faster. All right, so it's just getting perpetually steeper is one of the things that I want to notice. Yep. But if I was imagining going to the left, it's getting steeper and steeper that way, and it's getting steeper and steeper that way. But yeah, if you're right, if I'm coming down from this, it's decreasing, and it's getting less steep. And then it starts getting even more steep from there. All right, so that's called a parabola. Now, if I wanted to graph x squared plus 2, how about this? Let's see if I can make... Do I have space for a third column here? Did I write the word parabola in my way? For g of x, over here. And all I would do is take all of those numbers and add 2 to them. Right, so 0 plus 2 is 2. 1 plus 2 is 3. 4 plus 2 is 6. 9 plus 2 is 11. And it's the same in this direction. Right, so you guys see for g of x, just this plus 2 is just going to add 2 to all the y values. And if I plot these points, 0, 2 is right here. And I'd have 1, 3. 1, 3. And then I'd have 2, 6. And I'd have 3, 11. And then those are mirrored over the same axis of symmetry is what that's called, by the way. Let's see. So I'll draw the other parabola. Man, I'm not the greatest at that, am I? That's all right. And what do you notice about the purple parabola? That's their question. What do you notice about the purple parabola compared to the blue parabola? It looks like it was just a vertical shift by how many units? Every point is shifted up how many? No? 2. There we go. Right, so this plus 2, this plus c, results in a vertical shift. However, I am actually more interested in you guys learning some other stuff from this graph. All right, so this is called a parabola. Let's talk about this for a little bit. And I'm going to pull back to this as we need to. But it's a quadratic function. Quadratic functions are nonlinear. They're not a line. Notice how the curve was not a line. And it can be written in standard form as y equals ax squared plus bx plus c, right? So there's a quadratic term here. where a is not equal to 0, because if that was 0, then the first term is 0, and then we're back to a linear function. All right, mx plus b. The U-shaped graph of the quadratic function is called a parabola. By the way, the U-shape idea is a little bit deceptive because it almost sounds like this graph is at some point going to just go straight up, but it doesn't. All right, it's getting steeper and steeper, faster and faster. So it's ish. Yeah, kind of the U-shape describes a little bit more of the base of it, as it's not pointy like an absolute value graph. Yeah, exactly, yeah. It's called a parabola, and in this lesson you'll learn to graph quadratic functions where b and c are equal 0? Yes. All right, so yeah, where this and this are 0, and we will start by graphing these versions right here, where it's just a plain old x squared. Well, actually, that last sentence we'll do more tomorrow, and that's where, right, like I said, I did this a little bit out of order. So in terms of some vocabulary here, there's some interesting characteristics and terminology we should be aware of. The lowest point on a parabola is called a vertex, right? So that's the point where it changes direction. It's called a vertex. The line that it's a mirror over, I already used, was called an axis of symmetry. Brandon noticed that it was decreasing on kind of the left half, and it's increasing on the right half. And I'd suggested that it's getting steeper and steeper, faster and faster. All right. And in terms of that, let's see, I think we'll, yeah. Let's take a look at this example one, and it's going to be a little bit weird because we've got multiple examples here. But in terms of parabolas, they've got some interesting characteristics and behavior. And so you guys already have this graph. Follow along with me if you'd be so kind. All right, so you can see that the function is decreasing here. Here, this graph is actually not on the y-axis like our previous one. It's possible to have a vertex that is off of the axis. The axis of symmetry would be the vertical line that passes through that vertex, which vertical lines are always x equals a number. And in this case, that number is going to be the x-coordinate of a point that this line passes through. Okay, so there we go. So you can see that. You can also determine the following regarding a domain and range and where it increases and decreases. So you guys also already have this information here. Right, so the domain is all real numbers. So the domain is the set of all x such that x, right, it's just everything. It goes from negative infinity to positive infinity. And even though this looks like it's going way high, you'd be like, oh, but does it ever equal 4 for x? And it does, because I can square the number 4, right? 4 squared exists, 5 squared exists, 20 squared I can do, that's 400. 10 squared is, right? Wait a minute, 10 times 100? Wow, that was weird. Wait a minute. I said 20 squared earlier. Yeah, okay, that's what threw me off, because I was going bigger and then I suddenly jumped back. Right, I could even square a million, or a billion, or a trillion, or a Google. You can square all of these things, and that's why the domain is all real numbers, including the negatives, right? I can square the negative numbers. And the bigger the number I square, the way bigger it's going to be for a y value. And so that's why it says the range is all real numbers greater than or equal to -2. Whatever the lowest point is on your vertex is going to be your range. So your range is going to be the set of all y such that y is greater than or equal, in this case, to -2, right? But it would be whatever the y-coordinate of your vertex was, which for a lot of the ones we look at today are going to be our, it's going to be at 0, 0. It's going to be at the origin. For our starting ones here, and then we'll shift them up or down a little bit. So yeah, and then you can see that it's increases. Let's see, y increases as x decreases. Let's see, Wow, that's a really weird way to put it. Huh. I would have said that y decreases as x gets bigger when x is less than -1, right? Up to the axis of symmetry, it's a decreasing function. And then after that, it's an increasing function. Y is getting bigger as x is getting bigger. There we go. There we go. Now, one of the things I want to talk about is the slopes of parabolas, which, like I said, it's getting steeper and steeper, faster and faster. But let's go back to this example. And with lines, we would do something like up 1 and over 1, right? And then up 1 and over 1. And this is already off, and up 1. And you notice that like these don't have a set slope. And so I'm going to use the word slope very loosely here because they aren't actually slopes. So I put slopes in quotes. But notice to go from one point to the next, notice this is going up 1, over 1. To get to this next point, how high do I have to go? I have to go up 3 and over 1. And to go to the next point, I have to go up 5 and over 1. And so if I think about my slopes, notice that it's going up 1 over 1, up 3 over 1, up 5 over 1, up, the next one would have been 7 over 1, and then 9 over 1. What does this pattern appear to be for those numerators? Those are the what numbers? What? They're increasing by 2. Yep, so you're both right. So these numbers are increasing by 2. More specifically, they're odd numbers. And so one of the things that I like to think about parabolas in terms of is that the slopes of parabolas are consecutive, meaning one after another, odd numbers. 1, 3, 5, 7, 9, 11, 13, 15, 17, etc. Okay? So consecutive odd numbers. And I've got a little graph with that on it for you. And for, actually, I think I'll be able to pull this up here. Desmos. Here we go. Here's a little graph. And you can see the slopes are going up 1 over 1, up 3 over 1, up 5 over 1, up 7 over 1. And that the slopes are going to be consecutive odd numbers. So when I graph parabolas, what I do is I find where the vertex is, and then instead of making a table of values, which you could do, but is not going to be as efficient, I move by my slopes. So up 1 over 1, up 3 over 1, up 5 over 1, up 7 over 1. And notice, even if I change the C value, let's say I have plus 2 here. Can I land on it? It's not going to let me land on it out. You crazy thing. There we go. Plus 2. Oh, I thought this was one of the ones I modified. Huh. Maybe it isn't? Intriguing. No, it isn't. Aha, that's fine, though. That these points are actually going to be going still up 1 over 1, up 3 over 1 as well. So whatever my vertex is, looks like I have to tweak this programming. I thought I did. Maybe I didn't save it earlier. That's too bad. Well, tomorrow it'll make more sense when we talk about steeper slopes of parabolas. All right, so let's get out of here. Leave, my friend. All right, so let's, so in terms of that, oh dear, I did airplane mode accidentally. Blast. Slopes of parabolas, they are amazing. So, so instead of going up by a consistent slope, think about your graph as going, right, up by consecutive odd numbers, that 1, 3, 5, 7. And then once I pick those points, I simply mirror them, right? So this one is 1 away from the axis of symmetry, so I would mirror 1 over here. This one is 2 away from the axis of symmetry, so 2 points over here would have been another one. This one is 3 points away, so 3 points over here. would be another one. And 4 units away, and so 4 units away over there. And then I can make a very quick graph, far more quickly than your book allows. So we're going to use those slopes to quick graph parabolas, which is so much better than making a table of values. And then one of the things they say, if you add C, it moves up. If you subtract C, it moves down. But you guys are all experts on that. So let's actually do our second example one. Super confusing. That's how we do it. All right. This is example 1 from 8.2. I might have to zoom out a little bit there. Bam, got it. And you guys already have a table here for us. Or a graph, rather. Now, a regular parabola is going to look like so, right? Its origin will be, its vertex will be at the origin. And then to find other points, I'm going to go up 1 over 1, up 3 over 1, and then up 5 over 1. So 1, 2, 3, 4, 5 over 1. And it's just a super quick way of graphing without having to do a table of values. I hate making tables of values. All right, and then let's mirror these over the axis of symmetry. So let's make a point over here. Or you could even think about it as going up 1, backwards 1, up 3, backwards 1, right? And up 5, backwards 1. And so here is my regular graph, my parent function. I missed it. That's fine. So there's f of x. And if I want to do x squared minus 2, the only difference is this minus 2 will be a vertical shift down. And whether I graph this by a parent function, which eventually we're not going to do that, all right? I'm just going to say start at 0, negative 2 for your vertex. 0, negative 2. And then the shape of this is going to be the same, okay? So from this point, let's have you guys try going up 1 over 1, up 3 over 1, up 5 over 1. And I'll walk around and see how we're doing. Have a sip of water. Oh, my leg fell asleep. From 0. How is it? Yeah, I spent like so much time trying to make individual graphs and figuring out how I was going to sequence this. But I think this is so much better than the book's way, guys. They were going to torture you. But I'm like, no, math is amazing. Not torture people with math. So, all right, from this new vertex, up 1 over 1, up 3 over 1, and up 1, 2, 3, 4, 5 over 1. And then the same thing, just mirror those points. Mirror, 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 mirror. And then I just draw the best parabola that I can. Right? Where it's getting steeper and steeper, faster and faster. Now, I've got this difficulty where, right? This side I actually have a really hard time with. But when I draw this curve, I'm actually better on this direction. It's not a bad idea to actually rotate your paper and then use your wrist as like a pivot point as you like draw that curve. Okay, so like if drawing one side of the parabola is easier than the other, just do that. Like literally just like turn your paper until you can like hit the arc that way. And then, you know, I might even actually draw this side coming down and this side going. So yeah, whatever way works is fine. What I'm going to care about most are these points. I don't care as much about your ability to draw a curve. I'll try to make it nice. I'd give you full credit for this curve. And I'm even going to leave it imperfect So that way you guys know that I know that you know that I would give you full credit for that graph. All right, let's see. Let's keep going. So here's these examples are from 8.2. And I've got graphs all set for you and for me. Here we go. Let's make them fit. All right, so two graphs side by side. Notice these are actually different scales. I got them lined up pretty good though. So for the first one, for problem 1, I think you guys have this one, right? Okay. X squared minus 5, where is the vertex going to be? Going to be shifted what direction? No. It's a vertical shift, so it's up or down. What does a negative 5 do? Yeah, so the vertex is going to be 0, negative 5. So let's plot our vertex first. So 0, negative 5. And then watch me move by my slopes. Watch me move by my slopes. Here we go. Up 1 over 1. Up 3 over 1. Right? Up 5 over 1. And hey, actually, do we have enough space to go up 7? Is it? Maybe. Oh, I might have had to crop the top to fit it on a page, maybe. But I can go 4 plus 7 is 11, so I can actually fit the up 7 over 1 in this case. No? Even though this was a negative 5? Did I make an error? I've got it right here. Ah, sad Mr. Watty. I will have to fix it. No. 8.2 problem 1? No, it goes down to negative 5. Oh, it goes from negative 5 to like positive 8-ish or something like that. So I cropped off the top. This one right here? Not yet. I'm starting with the negative 5. All right, and then mirror it and mirror it. And I could even mirror that one. Wow. And I'll draw my curve. Let's see. That's a sad-looking parabola, but I don't mind. And yeah, try to not have it be a pointy parabola. Oh man, this is the saddest parabola I've ever drawn. That's okay. All right, this one. What's the plus 3 going to do you think? Up 3? So my vertex is going to be the point 0, 3. And so up 3. And starting from that point, I'll move up 1 over 1, up 3 over 1, up, let's see, 5 over 1. And then I mirror those. Mirror. Right? And I can draw that not too shabby. Maybe I should use my mirror tool because I'm way better at the right hand side rather than the left hand side. Yeah, but like I said, if you plot the points correctly, that'll be what's most important to me. Most importante. Right, it's math. Math. All right, let's what if I have I'll show you today a negative x squared. And let's analyze what this will do. So the negative 8, that's going to tell me my vertex. Actually, I'll even label that with this. Vertex is 0, negative 8. So just like with slope-intercept form, y equals mx plus b, my b was my starting point. For parabolas, my vertex is my starting point. And then, in this case, I've got a negative 1 here, right? Negative 1x squared, negative x squared. So that's going to be changing my slopes in some way. So for my slopes, and I use that term super loosely, mathematicians are probably crying already that I'm even calling it that. Instead of going up 1 over 1, up 3 over 1, I'm going to go down 1 over 1, down 3 over 1, and down 5 over 1, etc. Okay? So that negative just changed the direction of the parabola, is all it was. So vertex is at 0, -8, so that's right here. And let's see, careful counting the scale here. Make sure you don't get thrown off by my scales I gave you. We're going to go down 1 over 1. Down 3 more. 1, 2, 3 over 1. Right, and I'm just moving by these slopes. So it's actually not that bad. Way better than making a table of values. And then down 1, 2, 3, 4, 5 over 1. And let's mirror it. Mirror. 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 Let's see. And then I'll just draw the best parabola that I can. Now, I got some of them. Now, this is what I would call an upside down parabola. Or I would say it opens down. Okay? Because of this, right? It's opening downward, kind of the direction that this swoop is looking, right? You could even say that where these arrows are going, because this does travel infinitely, it opens down. So if you ever hear that terminology, that is what I mean by opens down. All right, I think this video is as long as it should be. We've covered enough stuff. Our homework will shorten it up a little bit appropriately. Thanks for watching, Internet friends. Have a great day.